This video, we're going to talk about Cartesian vectors. And to be able to talk about Cartesian vectors, we need to talk about another couple of concepts before we talk about these Cartesian vectors. The first one is vector decomposition. As we're going to see, it is basically breaking down or expressing a vector as the summation of other two vectors. And the second one is unit vectors. Those unit vectors are going to help us define the direction of the components of that Cartesian vector. So first we're going to look at vector decomposition. Let's just start there. The idea is that if we have a vector, this is a vector F. Let's say that this is describing a force, and if I have two directions in which I want to express this vector as, or I like to call it, break it down into different components. Let's say that I have a direction that is like this, and let's say another direction that is that's probably not a good idea actually. That's most parallel to that vector. So let me see if I can go back. There you go. So let's say that we have a direction that is like this, and a second direction that might be like this. Okay, so we have two directions. They don't have to be perpendicular to each other, right? So what I can do is I can draw parallel lines to those two directions. One goes like this, the other one goes like this. And now what I can do is I can take this vector F and express it in terms of other two vectors. How do I do that? Well, using the idea of the heads to tails that we've seen in other videos. So I can have this vector, let's call this F1, and I can have this other vector F2 that is right there. Now what's happening here, now I'm saying that my vector F is equal to F1 plus F2. Right, I've broken down or decomposed that vector F into two vectors given a specific direction. Now, in most cases, what we're going to see for the rest of the semester is that we're going to break down, we're going to decompose these vectors into perpendicular components. So what we're going to see most of the time is that if I have my vector F, then I'm going to have my x and y axis, then what I'm going to see is that the components of this vector are going to be this, let's call this fx, and let's call this one over here fy, right? This is easy to do because we have a right angle here. And often we're going to have some type of angle to be able to define the direction of that force F. So we perhaps might have this angle theta, or we might have another angle, let's say over here, alpha. Right, so if we have any of that information, we should be able to use sine and cosines to be able to find fx and fy. All right, so that's the idea of vector decomposition. The main idea is instead of adding two vectors, you're kind of doing the opposite. You're expressing one vector in terms of the two components of that vector. Now, again, it's important to have the directions in which you want to decompose the vector to be able to do those calculations. And in most cases, those directions are going to be perpendicular to each other, right? Especially when we're looking at Cartesian vector form. All right, now let's talk about the second concept that is important to understand these Cartesian vectors, which is unit vectors, okay? So unit vectors are quite useful because they help us define the direction of a vector. They have no magnitude, they have magnitude of 1, that's what they're called unit vectors, and they have no units, okay? So let's write down those characteristics of unit vectors. So unit vectors, they have magnitude of 1, they have no units, and they also help us define the direction of a vector. And this is going to be more evident when we look at forces along a line. Right, one other thing that we want to know is we're going to use a small hat on top of the unit vector to indicate that it's a unit vector. So I'm going to use this symbol hat to indicate that is a unit vector. Okay, for example, if I have the vector u hat, now that is indicating that that vector u is a unit vector. So it will have no units, and it will have a magnitude of 1. Okay, very good. Now there are 3 unit vectors that are particularly of interest to us, okay? And that is the unit vectors that we are going to define along the x, the y, and the z axis. So if I have, let's say, something like this, right? And this is my x-axis, this is my y-axis, and this is my z-axis. Now what we can do is we can say, okay, just to make sure that we're talking about the right direction, I'm going to define a unit vector in each of those directions. Along the x-axis, we're going to call it I hat will be my unit vector. Along the y-axis, I'm going to call it j, that j hat. And along the z-axis, you probably guessed it already, it's going to be my k hat. Okay, at this point, I often get the question of why do we go to all the trouble of saying I, j, k? Why don't we say x, y, and z? And the reason is because we cannot do operations with axes, but we can do operations with vectors. So making that distinction is important. We're going to see how important it is later on. Okay, so we're looked at the vector decomposition. We look at unit vectors, and let's put these two things together to be able to express a vector in Cartesian vector form. And that's basically using those unit vectors I, j, and k. So let me go here to my next page. And when we have these Cartesian vectors, we're going to have is we're going to define those Cartesian vectors in terms of the components along the x, y, and z direction. X, Y, and Z axis, right? So, or in other words, we're going to be using these I, J, and K unit vectors. Okay, we're going to be using that I, J, and K unit vectors. Give you an example. And I'm not going to do the calculations. We're going to see another video too that shows some calculations. This video is just for concepts. Let's say that we have my y-axis, have my x-axis, and I have a vector here, and this vector is going to be somewhere in this direction. Call that vector f. Okay. Now I want to write this down in Cartesian vector form. Let's say that we have information about this angle. And what I can do now is I'm going to form this right triangle right here. And I'm going to break down or decompose that vector into two other vectors. One going in this direction, one going in this direction. This is called fx. This is called fy. Right? If I have the magnitude of that vector f, I can calculate the fx and the fy, the magnitude of those vectors, by using sines and cosines. So what I will say is that the magnitude of this fy, right, the magnitude of that fy is going to be the magnitude of f times the sine theta. And if you don't remember well sines and cosines, I do recommend you go back and review this material. That we're going to use this for the rest of the semester. And for fx, the magnitude, right, is going to be the magnitude of f times the cosine of theta. Very good. Now, that's just the magnitude. I don't have a direction quite yet. So what I have to do in that case is multiply by the unit vector going in that particular direction. So I can say that my fy is going to be my magnitude of f sine of theta. Now I need to give direction to this, right? And the direction is going to be, since it's going up and down, is going to be j. So j hat. Important to have that unit vector there, right? So again, this part over here is my magnitude. This part over here is giving me my direction, right? Now when I have this fx, we have that this is the sine of theta, and now my unit vector is going to be I hat. So again, this is my magnitude, and this is my direction. Right? All right, now look at this f. We can say that f is fx plus fy, right? And since we have all of those written in terms of that magnitude and direction, I can finally say that my f, write the whole thing down. So my f is fx plus fy. And we can look at that based on that diagram and what we studied before in terms of the heads and tails method or the parallelogram law. That's basically what we're saying, right? F is equal to fx plus fy. And we can also write this as the magnitude of f times the cosine of theta I plus magnitude of f cosine of theta I plus the magnitude of f sine of theta j. And of course this is going to have some type of units like kilonewtons or something like that. All right, let me give you a very important thing that I need to mention, which is the equation that I just wrote down doesn't always work, because it's going to depend on what angle is given in the problem. So it is not always going to be the magnitude times the cosine ji and the magnitude times the sine j. So you really need to learn, go back and review the sine and cosine concepts, so you're able to write down the appropriate equations to break down your vectors, right? So that's something that you need to be mindful of.